Today, we're doing something truly fascinating. We are going to move past the perceived magic of artificial intelligence and academically deconstruct the rigorous computer science and mathematical principles that actually power modern multimodal generative systems. Think of this session as a masterclass where we pop open the hood of the AI engine to see exactly how language and perception are being bridged. Here's our syllabus for today. We'll be defining multimodal AI, breaking down the generative AI pipeline, demystifying diffusion models, looking at the art of prompting, examining failures and inherent bias, and wrapping up with safety and real-world impact. Let's get right into it. Section 1. Defining multimodal AI. Let's start by establishing a very precise definition of our core subject. So, what exactly is it? Well, multimodal AI represents a massive leap forward. Unlike traditional AI, which typically operates on just a single modality, like a text-only language model or an image-only classifier, multimodal systems are entirely different beasts. They inherently combine language, visuals, and context to convey meaning, processing and generating across multiple data types all at the exact same time. The ultimate goal here is to replicate the rich, highly nuanced way that human communication actually works. Notice how this centralized node connects text, video, audio, and images together. By pulling all these distinct data types into a single, unified framework, we're creating a robust system that mirrors how human perception operates in the real world. I mean, when you talk to a friend, you aren't just parsing their words, you're reading their expressions and listening to their tone. Multimodal AI aims to replicate that exact multisensory integration. Section 2. The Generative AI Pipeline. Let's look at the underlying technical mechanics that make this cross-modal generation possible. Think of the text-to-image pipeline as a transformation engine. It translates abstract language into concrete visuals. Step 1 starts with your natural language input. In Step 2, a text encoder translates that semantic interpretation into a compressed mathematical workspace. Step 3 feeds that data into the generative engine, which finally yields Step 4, your output image. It's this beautiful sequential journey straight from words to pixels. Now consider the mathematics of the latent space we're operating in. The model doesn't literally understand the phrase red apple as a grid of pixels. Instead, it maps semantic meaning to specific numerical vector coordinates, say 0.8, -0.2, 0.5, within a highly compressed multidimensional grid. Operating mathematically in this latent space allows the AI to capture and manipulate high-level features like shapes, colors, and textures with incredible efficiency. Section 3. Demystifying diffusion models. Let's explore the physics-inspired mechanics of the generative engine itself. Alright, let's really dive in because this is where the core engineering magic happens. The most accurate metaphor for a diffusion model: imagine a sculptor carving a statue out of a block of pure randomness. The system literally starts with completely random latent noise. It then uses your text prompt as the blueprint. Through a highly sophisticated mechanism called cross-attention, the model constantly references your words to guide its sculpting process, slowly pulling visual features out of the static to produce a structured, meaningful shape. And the way it learns to do this is through symmetric forward and reverse noise processes. During the training phase, a forward process systematically adds noise to a crisp image step by step until it's completely destroyed into static. It's essentially learning how a cake is made by meticulously unbaking it. The system does this to learn the exact mathematical distribution of that noise. Then, during the generation phase, it reverses the entire process. It starts with pure randomness and iteratively reconstructs the image, denoising the canvas under the strict guidance of your text prompt until that final output emerges. You might be wondering, why use this specific method over older technologies like generative adversarial networks or GANs? Well, even though diffusion models require computationally expensive, iterative steps and are generally slower, they offer vastly superior training stability and incredibly granular output control. In computer science, stability and control are paramount, and diffusion models deliver that beautifully. Section 4. The Art of Prompting. Understanding the engine naturally leads us to how we control it. To effectively guide the cross-attention mechanism we just discussed, simple queries just aren't going to cut it. Multimodal prompts need structural integrity. They must explicitly define key semantic parameters. For the best results, you need to clearly articulate the subject you want, the specific artistic style, the setting or background, and the lighting conditions. Precision in your language directly correlates to precision in the latent space. This kind of structured prompting enables incredibly powerful bidirectional translation. We aren't just limited to text-to-image generation anymore. By bridging these modalities, we can input a visual image and have the model generate text, acting as an image-to-text captioning tool. We can even input both text and a reference image simultaneously for enhanced reasoning. The system fluidly translates meaning across entirely different data forms. Because of this immense versatility, the current landscape of commercial models is now highly specialized. DALL-E 3 is exceptional at text understanding and safety. Midjourney offers unparalleled high-quality artistic and stylistic control. Adobe Firefly, on the other hand, focuses on commercial-safe, legally robust generations integrated straight into design software. As researchers and users, knowing exactly which specialized tool to select for your specific workflow is crucial. Section 5. Failures and Inherent Bias. As analytical thinkers, we must adopt a critical lens to evaluate these systems from a structural perspective. The generative process is not perfect, not by a long shot. When those semantic vectors in the latent space fail to map perfectly to visual features, we see profound alignment failures. Take a classic failure state like a mangled bicycle. If it has missing spokes, merged attributes where the frame literally melts right into the tires, and geometry that completely violates the laws of physics, the model has failed. It didn't flawlessly associate the word bicycle with the logical scene composition required to build a functional one. But the most crucial point is understanding the origin of these outputs, particularly regarding bias. When a model outputs a narrow stereotype, it is vital to understand that this is not a glitch in the code. It is an entirely accurate mathematical reflection of skewed training datasets. If a dataset is 90% dominant representation and only 10% minority representation, the latent space is structurally unbalanced. Those stereotypical outputs, that's just the algorithm faithfully reproducing the statistical environment it was trained on. Section 6. Safety and Real-World Impact. Let's conclude our lecture by examining how the industry mitigates these profound risks. Because these highly realistic models carry significant risks, think deepfakes or misinformation, engineers must implement a multi-layered security pipeline. This generally works in 3 stages. First, dataset filtering removes toxic data before the model even learns it. Second, prompt restrictions block explicit or dangerous terms at the user input level. And third, safety classifiers analyze the latent output to catch and block anything harmful before it ever hits the user's screen. When these ethical and technical safeguards are properly balanced, the results are nothing short of revolutionary. Multimodal systems act as powerful accelerators across global industries. In healthcare, they are analyzing complex medical images alongside patient data. In education, they are creating auto-diagrams and accessibility captions. In the creative fields, they allow for rapid prototyping and highly scalable personalization. They are fundamentally changing how we interact with computers. Class, as we wrap up our deconstruction today, I want to leave you with one final, critical thought to ponder. We've looked at the beautiful math, the latent space, the physics of diffusion, and the stark statistical reality of our training sets. As these powerful engines fundamentally alter human-computer interaction, how will we, as developers and informed citizens, ensure they actually augment human potential and creativity rather than merely reflecting our societal flaws?